I'm Professor Brad Fulton, and welcome to my Stats podcast. This is an edited audio recording of my course. Each lecture is its own episode, and there's a total of 24 lectures. This course provides an introduction to the quantitative methods social scientists and data analysts use to collect and evaluate empirical data about society. Through this course, you will learn to gather, describe, and analyze data with an emphasis on the application and interpretation of these methods. This course will also help you to be a more informed and critical reader of academic research, public opinion polling, and advertisement claims that present statistical evidence. Although some of the current events I reference might be dated, the content is timeless. I hope you enjoy this lecture, and if you have any questions, you can email me at bradrfulton@gmail.com. Hi, my name is Professor Fulton. If you like this podcast, you'll love the book I use for the course. It's titled Statistics, Unlocking the Power of Data. This book uses a highly intuitive approach to help students visualize statistical concepts, which accelerates understanding. I've reviewed dozens of textbooks, and Unlocking the Power of Data is hands down the best one out there, mainly because of its unique intuitive approach and straightforward explanations. You can find a link to the textbook in the show notes, and if you use the promo code BLOCK5, you'll get a 10% discount. This will be key not only for the assignments, but especially for the exams, and it's easy to get tripped up on, but read the questions and answer the questions that are asked. Some of you guys did more work than was needed because you answered questions that weren't even in there, and then you neglected to answer the question that was being asked. And so good practice is with the assignment, figure out what is it that they're asking for, and just answer that precisely. Especially with the exams, because you only have a limited number of points that you can get, and if you don't answer the question, I can't give you credit for it. And if you answer a question that wasn't asked, we don't give credit for that either. The exam questions are going to be very similar to the problems you're doing now. I just have noticed that with both Part 1 and Part 2, half answering or answering stuff that wasn't asked. Here's a thing that came up from the assignments is that experiments eliminate confounding variables. Like if we want to know if caffeine consumption affects exam performance, we could do an observational study, and at the beginning of the exam we could just say right at the top, did you have caffeine this morning? And say we found a relationship between caffeine and exam performance in the observational study. We couldn't make a causal claim about that relationship because there's all these confounding variables that could be affecting it. I think Brittany said staying up late the night before studying, or just a whole range of stuff. But if you do an experiment, what the experiment does is it takes all these confounding variables and eliminates them from the equation because we've randomly assigned who gets the caffeine. Some of you in the assignments had said, there's a question about, hey, we ran this experiment, can we make a causal claim? And some of you said, no, because there's confounding variables. Or some of you said, yes, you can make a causal claim, but you'd want to take into account the confounding variables. And so technically, if you run an experiment, the confounding variables are eliminated. So you don't need to worry about them, and you can make a causal claim. I know this can be confusing. Are there aspects of this that either just don't make sense, or questions that you have related to that from doing the assignment? Okay, here's another one that's come up. You guys have done a great job of digging into the GSS and finding variables, finding new variables. One thing to keep in mind is that this is a survey of people. So in a sense, you could be one of the people in this survey. And the questions that they ask are different types of questions. So sometimes they're asking you about your attitudes or beliefs about things. So like Rachel has a variable called single parent. And it's asking, do you think a single parent can raise a kid as well as two parents? Now, that question is asked to every single one of the people, but it doesn't let you know whether that person is a single parent or a double parent or not even a parent at all. So when you're finding associations between this question and you try and match it with, like, say, the number of kids they have or something, they might have 0 kids, because this is just a question about attitudes. It's not a question about, are you a single parent? So the best way to figure that out is to look at the actual question that was asked. And then there's a lot of questions about the person's characteristics, like how many kids do you have, how many siblings do you have, what's your income, all those things. But then there's also questions about significant others or spouses. And so you want to make sure, is this question being asked about the individual or like their spouse or their friend or things like that? Especially as you move forward with the research paper, you just want to know that you're picking the right variable and that it's measuring the things that you think that it's measuring. Okay, so the part 2 was to find sample statistics for one categorical variable and for one quantitative variable. Do you guys want your assignments back? I'm going to have each of you share one. Rachel, can you pick one categorical variable? Briefly, give the variable name, the question related to it, and the sample statistics for the categorical variable.
Oh, I didn't write that.
Tell me what you have.
I just take the graphs off and stuff.
Okay. For a categorical variable, the statistic that we're most interested in is the proportion of people who fall into each category.
Okay, so the first one I did was I just looked at, there was a medical study about people who had back pain, and I just did it for gender, who had more.
What proportion of females had back pain?
27% did, and 72 didn't.
That's good. Perfect.
All right.
And then, McKay, give me a quantitative variable, if you have one.
This one's how many hours a week do you use your email?
Okay.
The mean was 4.5, and the median was 2, and it's right skewed.
Perfect. Very good. Okay, you can pick quantitative or categorical.
I'll do categorical. I did hair color.
Okay.
And there was this study which is brown hair. So it was 8.8% were very dark brown, 27.2 was dark brown, 46.3 was medium brown, 13.9 was light brown, and 3.7 was very light brown.
You could do some good sociological research on hair color and certain outcomes. Very good. Brittany.
I had a quantitative one. It was hours spent doing those acts outside of the home in the past month. So it was they had examples was going to church or doing Bible studies like that. And the mean was 6.34 hours, but the median was 0 hours, which I thought was interesting. So the skew was right.
Okay, so and how do you interpret that? A mean of 6 and a median of 0.
Especially looking at the high numbers, there were a few people that spent a lot of time, 20 hours, 25 hours, but there was the high majority of people spent 0 hours doing it. So those few people that spent so many hours, because it was based on hours, really pulled the mean up, because there wasn't many people around 6 hours. It was pretty drastic.
I see.
A lot of hours or not a lot of hours.
Okay, yeah. Would you say less than 50% spend 0 hours, or more than 50% of the people spend 0 hours?
More than 50%.
So if the median value is 0 hours, that means that's the middle point. That means 50% of the respondents said 0, or it could even be more than 50%.
I did income, and I wasn't sure if it was categorical or quantitative.
It's important to know what the variable is. You see income, you're okay, but then you want to see, is this hourly wage? Is this it could even be a categorical variable.
Because they separated the income into brackets.
So
it was one was, because I had the same thing, 10.2 was the mean, and that was 15,000 to 20,000.
Okay.
So I didn't know what that would be considered.
Yeah. If it's already in that form, that means it was a quantitative variable that they converted into a categorical. So then, because your answer would be maybe 5, and then you have to go and see what does 5 correspond with.
That's why I wasn't sure, because I know most categorical, the mean doesn't mean anything, but with this one you could still.
You could sort of figure it out, yeah.
A good question. So I was looking at one of them, and I didn't know if it was quantitative, and I did area, and it was 2.6 mean and a 3 median, but it looked symmetrical. Is that because it's not 3 and 3? Is it not symmetrical? Because I looked at through the eye, just looking at it, and it wasn't that much difference. One in the middle, and then 2 or maybe this much difference on the left and right. I don't know if you have to
It doesn't have to be precise. Okay. The mean and median don't have to be exactly the same. And that's why visually you can look at it and see, is it look symmetrical or not? And it's oftentimes rare that it would actually exactly line up, but then you can look at it visually, or there's ways to do a quick test to see, is this a symmetrical distribution? we'll move on to this lecture, and I will forewarn you, from this point forward, the mathematics of this course will be stepping up. But I've tried to make these slides such that I don't just give you the question and the answer, but I show you the steps in between. So afterwards, if you're trying to figure out, well, how did he go from here to there, a lot of the steps will be mapped out on the slides. But you just got to make sure you understand step 1 and how you got to step 2 to step 3. We're describing data, looking at distributions and relationships. Can someone give a quick definition of what distributions are? Brittany.
It's like how the data is, I don't want to say distributed, but what we were just learning on. So if you graph it, how it falls or where most people respond.
Yeah.
If there's outliers.
Yep. So it's how the values are spread out across the x-axis. Yeah, all the values of the people in your sample or units in your sample. Okay, so we're going to look at one quantitative variable, and what we looked at on Friday was shape and center, like measures of the shape of the distribution and also the center of the distribution. And then today we're going to look at the spread, the measures of spread. Now this is probably one of the most important concepts, but also fairly intuitively inaccessible. It's not something we think about very much, is standard deviation. We think about mean and average, but we don't think about standard deviation. But this is critical that you guys understand what standard deviation is measuring. But generally speaking, it's measuring the spread of the distribution. So the sample deviation, which is italicized S, measures the spread of the distribution. So here's the formula for this. The little s here is notating standard deviation, and then this symbol here is called the summation symbol, and it sums up all the values in here, and then you divide by n minus 1. Anybody, what's small n referencing? Sample size, perfect. And then what is x bar? Anybody remember what x bar is, Brittany? Sample mean, very good. And then what about xi? Someone different from Brittany. What is x referring to? Just the variable.
Because you're the individual person.
Yep. So I goes from 1 to n, and n is the sample size. So if you have 100 people in the sample, this little counter is going to go I1, I2, I3, all the way up to 100. It's saying for each value in the sample, which is right here, how much does it deviate from the sample mean? So if we're doing age, but we won't use this class as the sample, but let's say we do age and the sample mean is 40. You could take yourself, who is 20 in here? Okay, so Chris, just in here, how much does Chris's age deviate from the sample mean? Sample mean is 40, his age is 20. 20, okay. You'd be taking Chris's age, subtracting it from, it'd actually be minus 20, right?
Yeah.
Subtract it from the sample mean, and then you're going to square that value, and then go on to the next person. Fortunately, your computer will do this for you, but you need to know what it's calculating. So then the standard deviation provides the average amount the values in the sample deviate from the sample mean. I'm probably saying this 100 different ways, 100 different times. Deviation is how much do you differ from the mean, but that's what it's measuring. So the reference point is going to be the mean, and then how close or far away from that mean is that value. So then you're going to take all the values in the sample and collectively say, are all the values squeezed close to the mean, or are they spread out? I'll do a quick example. In this class, if the class was the sample and we're looking at the standard deviation for the age of the people in this class, would the standard deviation be large or small? How much does each of your individual ages differ from the sample mean age? Chris?
1 year. I mean, I guess,
okay.
Isn't it because of 1 to 18 ones, you said it means 19, right?
Yeah.
20, so everyone's 1 off.
Yeah. Compared to if we did a sample of Durham, which standard deviation would be larger, this classroom or the Durham sample? So the Durham sample, because there's just more variation in the values, whereas in this class it's really tight around the mean. And we'll keep walking through this. The standard deviation is always greater than 0. So you never have a negative standard deviation. And even with Chris's example of his age being 20, which is 20 below the mean, because we square it, that gets rid of the negative value. So the more spread out the distribution is, the larger the standard deviation will be. So this is an example of our classroom ages where all the values are compressed. They're really close to the mean and they kind of hover around the mean. Whereas this example, the values have a much broader range and are more spread out. And so the standard deviation for this one is 4. So then this is an important mathematical truth or rule. If a distribution is symmetric and bell-shaped, then approximately 95% of the data values will lie within 2 standard deviations of the mean. So a standard deviation is measuring how spread out the values are. And so along this axis, if you go out 2 standard deviations in both directions from the mean, 95% of the people will fall in within that range. Yeah.
So that was a bigger bell curve. Us was 4.
Yeah.
So 2 standard deviations would be 8.
Yes. Yep. The reason why that would work is because if you spread it out further, this is going to go down, and so the 95% range will still be the same. It's basically saying this is a quick way to capture what is 95% of the respondents, where do their values fall. Once you know the standard deviation, you can do a quick calculation to find out where 95% of the people fall, and this will be important for further on in the course. We'll do a quick practice of this. So here's our distribution of data. You know, a way that these curves are created is like a dot plot. So there's data points. Since it's symmetric, the most people are going to fall right in here because there's going to be that many dots stacking up. Looking at this, what is the sample mean for this distribution? So these are heights in inches. What's the sample mean, Chris?
64.5.
64.5, perfect. Okay, so next, this one's more tricky. What is the standard deviation for this distribution?
7.5.
Okay, how did you get that?
I don't know, I just went like 72 minus 64.5.
And why did you pick 72?
It was the farthest out of that.
Okay. Oh, so you're thinking the range.
Yeah.
Okay. Were you going to try, Brittany?
Yeah, 5.
5. Okay, how did you get 5?
I took 69.5 and subtracted 64.5.
Okay. Approximately 95% of the data values will lie within 2. So you were getting it.
So it'd be 2.5.
2.5. So how do you get that?
You take the difference between the mean and not like 69.5 and divide it by 2.
Okay.
Or I guess you could just do like
67, yeah. So that's how you can just do it just by looking at a graph. You'll never have to plug the numbers into that formula, but you'll need to know how to get to the standard deviation looking at things like this. Okay, what is your height if it is 2 standard deviations above the mean? So someone in the front row.
69.5.
Boom, he gets it. Good job. How'd you get that? Okay, you just know it.
I mean, I just added 2.5, so it's
Because 2.5 is what?
that's the same.
Okay. What that's saying is a person with a height 69.5, it shows you where they fit in the distribution. They fit right on the edge of the 95% range. Whereas if the height was 67 or in here, you know you're in the middle of the distribution. This is good. You guys are beginning to grasp it. So, yeah.
I have one question about
Yep.
that last slide. So will it always like say like 95% up there if you're looking at the graph like that?
No, it won't always say it, but what it will say is what the standard deviation is. So let's say it says the standard deviation is 2.5. You will know, okay, I can go out 2 standard deviations, and whatever this value is, I can go up, and I can then go out this way, 2 standard deviations, and go up, and you can create that 95% range. So more often, it'll tell you what the standard deviation is, and then you can just go to that point, almost literally draw lines and say, okay, 95% of the values fit within here. Good question. So z-score, this is another term that's going to come up that you probably don't use in everyday life. You don't ask what's your z-score, but it's the number of standard deviations from the mean. My height z-score is about negative 2.5. What does that mean?
Below average?
Yeah, I'm a little below average or a lot.
95%.
I'm not even in the bottom 5%. if 95% of the values are within 2 standard deviations, and my height is negative 2.5 standard deviations, that means I'm really short. So that's my z-score. So like all of you have a z-score for your height, for your weight. It tells you where you fit on the distribution. When someone says, what's your z-score, what they're asking is, whatever your value is for what's being measured, where does it fit on the distribution?
It's kind of like when you go to the doctor's office and they're like, you're 97% above.
Yes.
Okay.
Yeah. In fact, so like my son is in the 10th percentile for height, and people are like, oh wow, he's only in the 10th percentile. I'm like, he's doing awesome because I'm only in the 3rd percentile, so he's like off the charts. But yeah, it's exactly that. It lets you know where you fit in relation to the other scores in the distribution. So a value z-score indicates how far it is from the mean. So in a sense, me being negative 2.5, I know that I'm 2.5 standard deviations from the mean. Here's the formula for z-score. And I'm only showing you the formulas that you need to know, so I'm not giving you superfluous formulas just to overwhelm you, but these are the ones that you'll need to know. Can someone take a stab at interpreting this formula? Chelsea?
X, I, for each value.
Uh-huh.
And then X bar is the sample.
Sample mean. So like during the exam when Timothy all of a sudden goes, it'll be a signal to everyone, use the mean.
Yeah, sample mean, and S is the standard deviation.
Yes. So with z-score, you're finding the position for a specific value. In these cases, the I will be whatever person you're wanting to measure. So if I want to know Brittany's z-score, I would put in Brittany's value here and see how it compares with the sample mean, and then divide it by the standard deviation. So everyone has a corresponding z-score. It's a unit-free measure of extremity of a data point, and what that's saying is that you can compare z-scores even if people are using different units of measure. Say we want to compare with people in Europe and they're using centimeters for height. Do we need to convert? You actually don't, because the way that this is designed is it's a standardized score that doesn't depend on what units you're using. Yeah?
So can you compare related values as well? Like could you compare like the z-score of your height to your z-score of your weight?
Yeah, and there would likely be a correlation
Right.
between those, yeah. So then z-scores farther from 0 in either direction are more extreme. You know, you want to know where you fall in the distribution. If you have a highly negative z-score, you know you're way on the left side of the distribution, whereas if you have a high z-score, you're on the right side of the distribution. This 95% rule, 95% of the z-scores for a distribution fall between -2 and 2. So 95% of the people in your population are going to fall within -2 and 2 standard deviations from the mean. If you're within the 95% camp, or if you're outside of the 95% camp, you know you're extra special. We'll do a z-score. We're back at height again. What is your height if its z-score is 3?
72.
72 inches. Okay, how'd you get that?
Because we do one z-score for one sample deviation.
Uh-huh.
It's 2.5, so I just wanted to do.
Okay, so why wouldn't it be 57?
You just say -3.
Ah, perfect. Very good. The sign on the number tells you which direction you're going in.
Let's say like the z-score is
-3.
Would I work backwards?
Yep, because -3 is basically saying that it's 3 standard deviations below the mean. Okay, so standard deviation and z-score, you're going to see them all the time from this day to the end of class. We don't talk about standard deviation or z-score in everyday life, so it's really important to conceptually know what we're asking about with both of these. The standard deviation is measuring the spread of the whole distribution. It's looking at the whole sample, whereas z-score is looking at the position of a value on the distribution. Because you might get something that has a standard deviation of 1. Don't confuse that with a z-score of 1. they're measuring two different things. So the standard deviation is for the whole sample, whereas z-score is for a specific value in the sample. I have all these examples in here, and I'm just going to fly through these because I think we've done it pretty well. But you'll have them on the slides so you can go back and test yourself or whatever. Okay, so here's a real-life example. Duke University admissions office all of a sudden got a ton of applications, and half the students had ACT scores and half the students had SAT scores, and they're on different scales, different units, and so they're like, oh my gosh, how do we tell what score is better? Is an ACT score of 28 or a combined SAT score of 2100, which one's better between those two? And without using the standard deviation or the z-score, there's no way to find out because they're two different tests and they have two different measures. But this provides a way to quickly tell what score is actually better, a 28 or a 2100. The two pieces of information that are critical to know and that you'll always be given when you have samples is you'll be given the mean and you'll be given the standard deviation. And so if you have those two pieces of information, you can do a ton with the data. If I was going to ask this question, how would you begin to figure this out using the stuff that we just learned about standard deviation and z-score? Okay, I'll give you a hint. Which test score has a higher z-score? So the standard deviation gives you the distribution of all the ACT scores that are out there. And the z-score lets you know where on that distribution that point lies. It lets you know the position on that distribution. So remember we were talking about 95th percentile? It lets you know this value of 28 is one of the values in this distribution. And so if you want to find out where that fits on the distribution, you would calculate its z-score. So you take the value that you're interested in, which is 28, you subtract from that the mean, and you divide by the standard deviation. And so you get a z-score of 1.4, and then you do the same for SAT. So what's interesting is, the scale of these numbers is very different. A 28 and a 2100, it's like the 2100's got to be more, or you think about quantities, but because you're also subtracting the mean value, it's going to even it out. Which test score, which one is better, an ACT of 28 or a SAT of 2100? Brittany?
An SAT of 2100.
Why?
The higher you score means that it's further away from the, like it's higher than the average with the ACT score.
Yep. So with the ACT, it says that the average person gets a 21 on there. And so you want to know how much above average or below average are you. And with the ACT, you're 1.4 standard deviations above the average. Whereas this one, the person who got the 2100 is 1.85 standard deviations above the average. So they're that much better than the average. You guys are right. SAT score of 2100 is the better score. So there's other measures of location, but the most difficult one was the z-score. But here's some other measures of location. Maximum, we're looking at the sample distribution, and you want to look at a specific value, and this specific value is the largest data value. And then also would be the minimum. And then we have quartiles. These are specific points in the distribution. Q1 would be the median of the values below the median. To get the median, you cut the distribution in half and whatever the center point is, and then you could take the bottom half and cut it in half again and get Q1, which is the median of the values below the median. Q3 is the median of the values above the median. So you have max, min, and quartiles. So here's our 5-number summary. This is like a way to look at all of these measures of location together. So you have the min and the max at the extremes. You have the median, which is in the center, and then the quartiles, which are the halfway points below and above the median. So then the way this works out is 25% of the values are going to be between the min and the first quartile. The next 25% is going to be between the first quartile and the median, and then so on. Another measure of location would be percentiles. So the percentile is the value of a quantitative variable that is greater than p% of the data. Now this is a horrible way to define it, And I tried to figure out a better way, but there isn't. The better way to do it is just to look at an example. But it's like what Chris was talking about. If you're in the 95th percentile, it's indicating where on the distribution your value fits. So we'll use the SAT and ACT example. Z-scores can determine whether an SAT score of 2100 or an ACT score of 28 is better. Percentiles can also provide this information. An ACT score of 28 puts you in the 91st percentile. What does that mean? If I say that this score is in the 91st percentile, yes?
They have a higher score than 91%.
Yes. Their score is better than 91% of the people that took the exam. So 28 is greater than 91% of the scores. And there's tables that you can use where if you have the Z-score, you can see what percentile it matches up with. Let's say we had an ACT score that had a Z-score of 2, meaning that it's 2 standard deviations above the mean. What would the percentile be? 90. Yes. Yeah. What if the Z-score is -2? What would the percentile be? 5th percentile. So the score is better than only 5% of the population. So when you have a distribution of values, 95% of the values are going to fit within 2 standard deviations of the mean. And so if my score is -2 standard deviations, I'm going to go over 2. And basically it's going to be right at the 5% mark. But basically every Z-score corresponds with a percentile. And so there's tables where you can look that up, or you know some benchmark things of a Z-score of 2 corresponds with the 95th percentile. Okay, the SAT score of 2100 is the 97th percentile. Now you guys might not remember what the Z-score was for the SAT score of 2100. Give a rough guess of what you think it would be.
It should be greater than 2.
Great.
They only want
That's exactly right, that it would have to be greater than 2. We don't know exactly what it is, but because it's in the 97th percentile, we know that it's beyond 2 standard deviations.
Wasn't 3 standard deviation 99.7 in the first one? So
yes. Good job. Impressive. Again, these are measures of location for specific values. So whenever you're asking about percentiles, you're wanting to know, well, where does this value fit on the distribution? So 5-number summary, the slide that we just looked at. So the min, if you're the min score, if you get the absolute lowest score on the SAT, you can know that you're in the 0th percentile, that there's no one, you didn't get a score better than anyone. However, if you're the max and you're in the 100th percentile, that means that your score is better than 100% of the scores in the distribution. If you're in the 50th percentile, it means that you're greater than 50% of the people in the sample. And then the quartiles line up with the 25th percentile and the 75th percentile. Yeah?
How do they do it if there's like more than one person? Like if you get a perfect score,
yeah.
The max, but if there's 3 people with perfect scores, then they're not. Is it like 99.9%?
Well,
or
so,
still say 100%?
Yeah, all those values fit into that quadrant of the
Okay.
100th percentile because they're all the max. And sort of like with median, it's okay that there's more than one value. In fact, with the median, there will be a lot of people at the 50th percentile. So it's more so making sure, is that value the max value? And it doesn't really matter if there's other values that also share that amount. Okay, so then what's the predominant measure of spread that we use in this course? Standard deviation, yes. And what's the measure of location that we use in this course? Z-score, yeah. Z-score lets you know where on the distribution it fits. And so now we're going to look at how outliers fit into this whole equation. The range of values is the max to the min. That's the endpoints of the distribution. Then there's also a thing that's used is the interquartile range, and that's the 3rd quartile minus the 1st quartile. So it's like the middle 50% of values. These are just other measures of spread that we're looking at. So is the range resistant to outliers? Does anyone remember what resistant means? Resistance is how influenceable, how affected it is by outliers. So then is the range is the max and min. is that resistant to outliers? An outlier is a specific value. And so let's say we're doing this class and we do height and I write down Timothy's height wrong and I give him a height of 120 inches. That's an outlier value. And so if we looked at the distribution, the max would say 120, you'd be like, something's wrong with that range. That outlier is really affecting it. Whereas if we realize, oh, that was an error, and we remove that outlier, the range is going to go back to what would be expected. IQR, which is the interquartile range, is that resistant to outliers?
Yes.
Perfect. So the IQR is not affected by outliers. An outlier can be informally identified by looking at a plot. So through no mathematical means or anything, you can say an outlier, you can just see it visually, like, wow, that looks like an outlier. There is a formal rule for identifying outliers, and it's basically, is the data value more than 1.5 IQRs beyond the quartiles? So if someone said, formally speaking, this is considered an outlier if it's more than 1.5 IQRs beyond the quartile. And that's really confusing, so we'll break it down. A data value is an outlier if it is smaller than this equation. So whatever your first quartile value is, minus 1.5 times IQR, and IQR is that interquartile range of Q3 minus Q1. That's just a formal definition. So when I say an outlier, and Chelsea says a value is an outlier, it isn't just my judgment against her judgment, but we're using a standard equation. So with box plots, this slide will explain everything, so I'm not going to go through it because I want to get to correlations. So we're going to move on to quantitative statistics by category. The statistics we calculate for a quantitative variable like height or weight can be looked at separately for each level of a categorical variable. So if we want to do this with the example of height in this class, so height is the quantitative variable. What's a categorical variable that we could look at within height? Chelsea? Gender. Okay. You take whatever quantitative variable of interest, height, income, education, and then you can look at it, how it differs by a particular categorical variable. Gender, race, religion. For this one, we're going to do quantitative variable is the number of hours spent studying per week. And then the categorical variable is going to be academic major. And so the mean number of hours spent studying per week by major is this. For arts and humanities, it's 16.2 hours. Social sciences, 17.5. And natural sciences, 17.8. This is beginning to see how quantitative statistics vary by different categories of people or groups in your data. And so this would be a thing that you'll want to do as you're looking at income and you want to say, does income vary by religion? You could look at the mean value. So this is like, of all the people in the arts and humanities, this is the mean value of hours they study. I should put the overall mean just so you can see, like, there's one above or below. You can also look at a relationship between two quantitative variables. So the example we've been using is height and weight, or you can use income and education. So you take two quantitative variables and you look at their relationship. A scatter plot is a graph of the relationship between two quantitative variables. Have any of you guys seen this before, or did you see it in the reading? Okay, so you'll see these a lot. I mean, this is one of the ways that you visualize data and look for patterns. But on the x-axis, you're going to have one variable, and this time we have number of hours spent studying. And then on the other axis is the variable that you're comparing it with. In this case, it's GPA. Each of these dots represent a different person, and you can tell their value by looking at where they fall on the graph. So each dot represents one case. So then the question is, do the dots form a clear trend? Do you see a relationship? Like as you go out on the x-axis and you go up on the y-axis, do the dots move in a certain direction? Not really. There's a scale or a continuum of a relationship. And there's a formal way to measure it, but this is just visually looking at it, that there is a slight upward direction. Not super strong, but you can see something there. And in this case, it's upward in the sense that the line is moving this way. It'd be downward if the line was moving this way. Are there any outlier points? He doesn't have a 4.0, yeah. And then there's this person who studies 10 hours. So there are some outliers, and that's important, and we'll get into that. But it's important to say, are there outliers? So then when we're talking about correlations or associations, a positive association means that the values of one variable tend to be higher when the values of the other variable are higher. So as height goes up, weight goes up. There's a positive association. A negative association means that values of one variable tend to be lower when the values of the other variable are higher. And so as one goes up, the other one goes down. And then no association exists between two variables if knowing the value of one variable doesn't give you any information on the other variable. Correlation, association, and relationship are all interchangeable terms. So correlation is the formal way to talk about it, and there's a mathematical equation to calculate correlation. So you don't just have to say, well, it looks like a relationship, sort of. You can actually quantify it. And so the sample correlation measures the strength and the direction of a linear association between two quantitative variables. Another formula. Does anyone recognize anything within here that it's measuring? Do you see some similarities? Z-score. Z-score. Let's see. You got it. Timothy is right on. He called it. So you're looking at the Z-score for X and the Z-score for Y. So there's some rhyme and reason behind these formulas and what they're measuring. Sx is the sample standard deviation for variable X, and then Sy is the standard deviation for variable Y. And basically, X is the one quantitative variable and Y is the other quantitative variable. You're mapping the Z-scores, and you're seeing, when you multiply them together, what outcome it produces. And I'll walk you through the correlation. So let's say height is X, the one variable that we're looking at. So you need the reference point. Mean height is 64 inches, and then X1, X2, X3 are the values in your sample, and it goes out to, say, 100. And then right here is the Z-score for each of these values, and that's what's going to be going in right there. So then if we look at weight, the mean weight is 180 pounds, and then Y1, Y2, Y3 is the weights in the sample, and then these are the Z-scores. And so what you'll be doing is multiplying 1.2 times 0.9, and then multiplying 1.8 times 1.3, and negative 1.3, negative 1.4. And that's this. And so what you see is, because every time the height has a high Z-score, what do you notice the weight having? A positive Z-score or a high Z-score. What happens when height is down and it has a negative Z-score? Yeah, and you're always looking at the value for one particular respondent. So you're looking at X3 is their height and what its Z-score is, and then you look at their weight and what that Z-score is. And so if there's a relationship, if the height has a similar Z-score as the weight, and all of the data values have that relationship, then you're going to know that there's going to be a stronger association. So positive correlation, R being greater than 0, exists when positive scores for X tend to occur with positive Z-scores for Y, and vice versa. So we'll end right here. So that is all.